one over there.
Okay, thanks Raquel for that. So, good night. I'm going to talk to you, well, we're going to talk to you tonight about inflation. And the main thing about inflation is it's one of the oldest processes that there ever is actually as old as something can get old. And we're going to tell you what it is, we're going to tell you why do we need it, and we're going to tell you how does it work. Great. So I guess to start, the main motivation for this would be there's something that it's actually quite normal to us. And when you think about it, it's kind of weird that it is normal. And that is that everywhere you look around at the night sky, it kind of looks pretty much the same, especially the further you look, the more self-similar it looks. And actually, hey, I just realized I don't have a clicker. Sorry, I just realized I don't have a clicker. So yeah, the farther you go, I know there's planets, they're not everywhere, but you go further out, there's stars, and they're like more similarly distributed. You go further out, and to the biggest scales that you could get, it starts looking very, very similar. Actually, the further you go, can I do this? Yeah. This is the light from the furthest we get to see. And it's pretty self-similar, as you can see. And that was actually quite a surprise. So when we first saw this, we didn't expect that necessarily. And we got to see, there was a time in which we actually measured the furthest light there is, and we saw, well, that's pretty similar. so why could actually explain that? And that's the motivation for this talk. That is what motivated inflation. And so, yeah, right. The main point being, okay, it looks like there's, everywhere you look around, it's more or less the same, but couldn't it be that you had more stuff to one side than the other? We weren't necessarily expecting it all to look pretty much exactly the same. So, great. How do you actually explain that? So there's 3 principles to explain that. The first one would be that information travels at finite speeds. The second, that the universe is a dynamical entity that accelerates and decelerates its expansion as time goes by. And the third one, that the energy one can have in the tiniest patch of space is finite. Now, does this actually explain anything? And the answer is yes and no. Maybe you're right now, as I say this, concocting explanations or how to combine those principles to explain that. But it's not so trivial. You're not used to playing with universes and energy and so together. So let's talk about it in terms of things that we have all actually played with. So colors and okay, I'm gonna leave that there for a while. Keep okay, and balloons. We've all played with them, right? Great. So now if we go back to our 3 principles, we can, maybe instead of information travels, we could say any end travels at finite speeds. That's a reasonable assumption. A balloon is a dynamical entity. It accelerates and decelerates its expansion as time goes by. And the number of colors that one can have in the tiniest patch of rubber in that balloon is finite. If you go really, really tiny, there's not that many colors in that tiny space. Great. So, now that we've identified the players, let's play. So they say that you had a party, and it was a really fun party. There was a lot of colorful balloons in your house, and there was a lot of beer, and it was all over the place. and end up on the balloons. And you wake up the next morning and there's ants. There's ants all over the balloons. They're all over the one balloon, especially there. So you could at this point just like shake them off and whatever. But instead of that, you decide, I'm going to inflate this balloon. Actually, I'm going to inflate it so fast that these tiny ants are not going to have enough speed to ever reach other parts of the balloon. It's going to be so that they're circumscribed to a really tiny monochrome patch of rubber. And you can do so for forever, but I mean, after a while, your lung capacity is going to run out. And then you're going to start decelerating. And as you decelerate, you can imagine that maybe now the ants can actually explore the different colors in the balloon. And so you might imagine that maybe another ant is going to come by and, you're going to run into them. Or maybe, you're going to explore the globe around. And you're going to go to other patches of the balloon and you are going to see different colors. And that's all things that it's pretty reasonable that you could do with ants and balloons and colors. And, okay. So a thing that I talked about, but I kind of like loosely talked about is it being faster than the ant, but actually how fast is fast? How fast does it need to be so that we actually outrun the ant and we get to constrain it a really tiny piece of the balloon? So say that you're a gentleman and you're like looking at an ant, so you're walking at the speed of the ant, which is 1 millimeter per second, more or less. That's nice. Say that now you kind of like get bored and you want to outrun the ant. So you would just like walk at a normal pace, 1 meter per second. Does this work in the image of inflation that we were just talking about? Great. So now we go to the balloon again, and the question being, how fast should I grow the balloon so that the ant gets constrained in a little tiny piece of rubber again? Great. So say that the ant is growing it's walking at 1 millimeter per second, and the balloon is growing at 1 meter per second. That seems like a reasonable assumption. We definitely outrun the ant walking at 1 meter per second. If we grow the balloon at 1 meter per second, does that actually constrain the ant to a little tiny patch? And the answer to that you might be expecting is no. Actually, that is not the case. Will the ant ever reach the place where it started? And if you give it enough time, doesn't matter how fast that speed is, the ant will reach the other end. The only way that you can actually constrain the ant to a tiny piece of the balloon is if you accelerate the rate at which the rate at which you grow the balloon. So it shouldn't be just 1 meter per second. It should be 1 meter per second squared, or 10 meters per second squared, or whatever you want. It could be even smaller than that. It just needs to be accelerated. Great. So then, the ant will be constrained to a tiny piece. Great. So now that we know the game, and we can actually go back and change the players. So let's change the ants to light, because that's the fastest thing there is. Let's change the balloon to the universe. And we're just the whole universe, further from what we can actually see. And let's change a tiny piece of rubber to our local, very flat, observable universe. Great. So if our picture of the universe is correct, the only reason that the universe is so homogeneous is because really early on we zoomed on really, really fast. We accelerated, actually, to a very tiny part of it. And it was so fast that we basically became isolated from everything else. And this period of time is called inflation, and that is why we came up with this, so that we could explain how flat that is. And I hope that was clear. So now with that, I'm gonna leave you guys and give the talk back to Robbie. R2D2.
All right, everybody hear me? Yeah, cool. So the first thing, I'm going to tell you guys a little bit how inflation actually works, so the mechanics of it in the early universe. So the first thing we need to talk about is how light travels in an accelerating expansion universe. So here I'm showing you two circles, a yellow and a red one, right? The yellow circle is light, and the red circle is the farthest distance that light ever reaches. And so we call that a causal horizon. So we say that just because nothing else can ever travel faster than light, right? So any ant that's trying to walk this distance can't make it past the red circle. Uh-oh. Oops. Well, you guys saw it, yeah. And so you might have noticed the light was slowing down a little bit, right? And the reason for that is the way I'm showing you this picture is the camera is zooming out at the same rate that space expands. So something that's a fixed distance in space will start expanding, but the camera zooms out, so it looks like it's the same distance the whole time. And so you'll get a better idea of how that works in just a second. So kind of the whole reason we're giving this talk is a few months ago we were playing around in Python, and we wrote a little game based on inflation in the early universe. All right. All right, cool. So you guys, at the very top of the screen, it says Inflation Simulator 9000. And you guys can hear our cool music we got. Cool, so let's start it. Let's see what happens. Cool. So there's a lot of things going on, and I'll try to tell you what's happening in a minute. So you can see we're zooming in to different colored patches, right? And so space is expanding. In the top corner there, you see a number. It says A of T. So that's the expansion ratio of the universe. So right now the universe is 3.5 times as big as it was when we started. And each colored patch represents one region that's mostly self-similar. So maybe the red regions all have one level of stuff in them. All the blue regions have a different level. Cool. So as you can see, if you zoom in for long enough, the screen will get stuck and be a solid color, right? So now I'm going to restart inflation. And now I'm going to place an ant. So now this ant, every 4 seconds in the game, the ant's going to send a light ray out. And this red ring here is the horizon the ant has when it started sending the first light ray. Cool. So yeah, this ant sends out its light rays, and it's kind of hard to tell, but they don't go as far the longer you wait. The ant kind of gets trapped in a smaller and smaller region. So now I'm going to press G. And so now the camera is zooming out at the same rate that space is expanding. So you can really tell the early light rays are really far out, but the later ones are kind of stuck in a tiny, tiny patch. That's all the same color, right? This is the whole idea of inflation, is that with an accelerated expansion, you can get stuck in a tiny, tiny region of space. So some other cool things can happen. So let's restart inflation, and now I'm going to place 2 ants. So right now, you can see the red circles overlap, so they can talk to each other. They're within each other's horizons. But now, if I click again, space has expanded and the horizons have shrunk. So now each ant has access to a smaller portion of the universe than it used to. So the other thing I can show you guys is this little plot. The white line there is the distance between the 2 ants. So in this view, space is expanding, but we're zooming out at the same rate, right? So that distance is constant the whole time. And the red line is the horizon length. So it drops down really fast with time. Yeah, if I click again, you can see how far it's shrunk. So I'm going to restart inflation again. And I'll place 2 ants again. So now these guys are within each other's horizons. They can talk. But as time goes on, they get more and more shrunk in. So now the 2 ants are in different patches of the universe. They can't talk to each other. And now I'm going to end inflation. So now there's no more horizon. The expansion has stopped accelerating. So now light can travel infinitely far if you wait long enough. And so you can see the red curve went off the chart. And so it says inflation is off the charts. Cool. So if we wait long enough, these yellow circles will actually touch each other again. Or I can press the enter key and make time go faster. Cool. So now the ants can talk to each other again. They're best buddies. Cool. Cool. So that was pretty fun to make. We both had a lot of fun making that. Let's see. There should be a picture on this one. Yeah, so the picture that's on this slide shows you the history of the universe. Yes, use your imagination, you know. But the important thing is this is really what we think happened in our universe. We think there is a period of accelerating expansion, and then that stopped. And so during the accelerating expansion, we zoomed into a really, really smooth patch of the initial universe. Then inflation ended, and the part of the universe we have access to got a lot larger, but still not too big. It's still pretty smooth, right? You saw from Maho's plots and pictures. But recently, the universe has started doing something weird. This dark energy has started to control the expansion of the universe, and it's accelerating again. So I can't show you my simulation because it would be a much larger horizon, but we now have a horizon again. So there's a finite distance we could send a light ray and have it reach. And so that's a little depressing if you think about it. And when the universe is 1,000 times its current age, we'll probably be stuck where our horizon is only the same size as our local cluster of galaxies. And won't be able to see all these pretty galaxy mergers and things. So that's disappointing, but nobody's sure if that's really what's happening, but that's what it looks like right now. So the last thing I should tell you is that if you want to play around with this, you're more than welcome to. Don't look at my code too much. It's pretty messy. Yeah, Maho helped me clean it up a little bit, but it's our code isn't that pretty. But if you'd like to play around with it yourself, you're more than welcome to. Yeah, so that's our talk. Thank you.
I'll hold the microphone with this one. You guys share the microphone for answers. All right, MC Spaxel and R2D2. Questions? since we're mirroring, I'm going to see if I can get this. That's still not working. All right.
Yeah, it's right.
That's unfortunate. All right, questions. Questions on inflation, the start of the Big Bang. All right, up front. Factor of acceleration is required to stay ahead of the curve. Repeat the question.
So I think the question was, what factor of acceleration is required to stay ahead of the curve? Yeah. So it turns out as long as it's accelerating and it lasts long enough, then you're okay. And so we think inflation was a really short, really violent event. So we think it happened in 10 to the minus 30 seconds about. So that's a really short length of time, and so you need a really, really fast acceleration. And the amount of expansion you get is also pretty big, so that's about a factor of 10 to the 26. So it's a 10 with 26 zeros. That's about.
All right, next question. Up in the top.
So the ones in the PowerPoint slides are Maho's beautiful work, just PowerPoint. And the ones in the game were this library called Pygame. It's used for making Python games.
But they coded it up themselves, so impressive work. All right, other questions? All right. There we go. Okay.
Right. So the question was, how do we know that the universe is going to keep accelerating in expansion? Right. And the answer is we don't know. Nobody's sure. What we can say is we can look into the past universe and see if the rate of expansion from this dark energy has been about the same or has changed over time. And it looks like it's always been the same.
All right, one more question.
So the question was, if you take your laser and shine it, how far will it go before it bounces back? So, right now I think the horizon distance is about a third the size of the universe. So if you send your laser far enough, it would get to about a third the length of the universe and then stop. Or the light beam would keep moving, but in comparison to things that we can see, it would look like it stops advancing.
All right, the deep follow-up to that question you could ask these two wonderful speakers afterwards. Let's thank them one more time.